Here's something nobody's telling you about artificial intelligence in 2026. It doesn't matter how sophisticated your AI models are, how much money you've invested in machine learning infrastructure, or how brilliant your data science team is. Because right now, as you're listening to this, there's a silent crisis building that's about to make all of that completely irrelevant. And it has nothing to do with algorithms or training data. The real bottleneck choking AI deployment isn't computational power anymore. It's something far more fundamental, something most tech leaders are completely unprepared for. We're talking about electrical power, raw energy from the grid. And if you don't understand why energy availability is about to become the single most important factor determining which companies succeed with AI and which ones fail spectacularly, you're already behind. In the next 20 minutes, I'm going to show you why the entire conversation about AI is shifting from model parameters to megawatts, and more importantly, what you need to do about it right now. Let's start with the fundamental shift that's happening beneath the surface of all the AI hype. For the past 2 years, every conversation about artificial intelligence has centered on model size, training methods, and capability benchmarks. Companies competed on how many parameters their models could handle. Investors salivated over which startup had access to the most advanced foundation models. But that entire framework is collapsing, and it's collapsing fast. The experimental phase of generative AI is over. We're not talking about chatbots anymore. We're not talking about systems that summarize documents or generate marketing copy. The transition happening right now is toward truly autonomous systems, AI agents that don't just respond to prompts but actually execute complex workflows with minimal human oversight. These are systems that can reason through multi-step problems, plan sequences of actions, and adapt their behavior based on changing conditions. Think of the difference between a calculator and a self-driving car. One waits for input and gives you an answer. The other navigates an unpredictable environment and makes thousands of decisions autonomously. This shift changes everything about how we need to think about AI infrastructure. When you're running chatbot queries, energy consumption scales linearly with usage. More queries, more power, but it's manageable. But autonomous systems? They're running continuously. They're monitoring environments, processing streams of data, executing decisions, and coordinating with other agents. The energy profile is completely different. And here's the critical part. This isn't some distant future scenario. Telecommunications companies and heavy industrial operators are deploying these systems right now. They're moving toward what's called autonomous network operations, where AI doesn't just automate predefined tasks but actually self-configures networks and self-heals problems without human intervention. So let's talk about the wall that everyone's about to hit. Imagine you're a European startup. You've developed an incredible AI agent system. Your technology works. Your customers are excited. You're ready to scale. And then you discover that the data centers you need can't get enough power from the grid to run your workloads. Not because the data center operators don't want your business, but because the physical electrical infrastructure literally cannot supply enough energy. This isn't a hypothetical. This is happening right now across Europe. Compute scarcity used to mean you couldn't get access to enough GPUs or TPUs. That was the constraint. But increasingly, compute scarcity is becoming a function of grid capacity. You can have all the chips in the world, but if you can't power them, they're just expensive paperweights. And here's what makes this particularly challenging: electrical grid infrastructure doesn't scale quickly. You can't just spin up a power plant the way you spin up a cloud server. Grid capacity is determined by decades-old infrastructure decisions, regulatory frameworks, and energy policy. Which means that in Europe especially, energy policy is rapidly becoming de facto AI policy, whether policymakers realize it or not. This fundamentally changes the competitive landscape. Access to foundation models is becoming commoditized. Open source advancements mean more players can run frontier-scale models. But energy supply? That's constrained. That's scarce. That's valuable. So competitive advantage is shifting from owning the best model to controlling energy supply and the training pipelines that use it efficiently. If you're a venture capitalist looking at AI startups, the question isn't just how good is their technology anymore. It's, do they have a credible path to the energy they'll need to scale? Because energy availability will determine which startups grow and which ones stall out, regardless of how brilliant their algorithms are. This energy constraint is forcing a complete rethinking of how we measure AI success. For years, the metric that mattered was capability. Can your model outperform the competition on benchmarks? Can it handle more complex reasoning tasks? But now, there's a new metric that's becoming equally important: energy efficiency. How much value can you extract per kilowatt hour? How intelligently can you deploy resources? Think about what this means for enterprise strategy. The competitive edge won't come from having access to the largest models anymore. It'll come from having the most intelligent and efficient use of resources. This is triggering a shift in key performance indicators. Forward-thinking enterprises are starting to prioritize energy efficiency as a primary metric alongside traditional measures like accuracy or speed. They're asking questions like, can we get 90% of the performance with 50% of the energy? Can we architect our systems to do more inference at the edge rather than in power-hungry data centers? Can we time-shift workloads to take advantage of periods when renewable energy is more available? This efficiency imperative also changes the ROI calculation for AI projects dramatically. Those horizontal AI copilots that got deployed everywhere, the generic assistants without domain expertise or proprietary data? They're failing return on investment tests precisely because they consume resources without delivering measurable productivity gains. The energy they require doesn't justify the value they create. Compare that to AI deployed in manufacturing, logistics, or advanced engineering. These sectors are seeing clear enterprise ROI because the AI is integrated into high-value workflows. An autonomous system that optimizes a supply chain or reduces defects in manufacturing can justify its energy consumption because the value it creates is tangible and measurable. Here's a concrete example. Imagine a logistics company deploying AI to optimize delivery routes. A generic model might reduce fuel costs by 5%. But an autonomous system with deep domain expertise, trained on proprietary data about traffic patterns, customer behavior, and vehicle performance, might reduce costs by 20% while also predicting maintenance needs and optimizing warehouse operations. The energy required to run the more sophisticated system is higher, but the value created justifies it many times over. That's the kind of efficiency calculation that will separate winners from losers. The energy constraint isn't just changing how we measure success. It's fundamentally transforming how AI systems are architectured. We're seeing a move away from monolithic models toward multi-agent systems. Instead of one massive model trying to do everything, you deploy multiple specialized agents that collaborate on complex tasks. Each agent is optimized for specific functions, which means you can use smaller, more efficient models where appropriate and only deploy computational heavy hitters when truly necessary. This architectural shift has profound implications. In telecommunications, for example, operators are deploying agent systems where different agents handle network monitoring, traffic optimization, security threat detection, and capacity planning. These agents communicate and coordinate, but each one is tailored to its specific domain. This allows for much more granular control over energy consumption. You're not running a massive model continuously. You're orchestrating multiple efficient agents that activate as needed. But this introduces new complexities, particularly around security and governance. When you have autonomous agents executing tasks and making decisions, you need robust frameworks for auditing those actions. What did the agent decide? Why did it make that choice? Can we trace the reasoning? As these systems gain more autonomy, they become potential attack vectors. Malicious actors could try to embed hidden instructions in data that agents process, essentially hijacking the autonomous decision-making process. So security priorities are shifting from traditional endpoint protection toward governing and auditing autonomous AI actions. You need to know what your agents are doing and ensure their decision-making processes haven't been compromised. This governance challenge extends to how we think about AI-generated outputs as well. We're moving toward what some experts call disposable AI. Instead of AI generating content that gets stored indefinitely, systems will create and refresh data on demand. Think of it like this: rather than having an AI generate a report that sits in storage consuming resources, the AI generates analysis when you need it, you use it, and then it's discarded. The next time you need analysis, the AI generates fresh output based on current data. This dramatically reduces storage requirements, which also reduces energy consumption for data centers maintaining massive storage arrays. Now let's talk about a dimension of this energy challenge that's particularly acute in Europe: sovereignty. When we talk about AI sovereignty, we're talking about ensuring that critical AI infrastructure and data remain under local control, subject to local regulations and protected from foreign access. This isn't just about data privacy, though that's part of it. It's about strategic autonomy, not being dependent on infrastructure and services controlled by entities in other jurisdictions. The energy constraint makes sovereignty more complicated and more important. If you're a European enterprise and you want to ensure your AI workloads run on European soil, subject to European regulations, you need European data centers with European energy. But European grid capacity is constrained. This creates tension between sovereignty goals and practical scaling needs. Some companies are being forced to choose. Do we maintain strict sovereignty and accept limited scale, or do we compromise on sovereignty to access the energy we need for growth? This is driving interest in sovereign AI solutions that leverage existing data center footprints. The idea is to create AI infrastructure that's explicitly designed to keep data and processing within specific jurisdictions. Survey data shows that an overwhelming majority of IT and AI leaders in Europe view enterprise open-source software as vital for achieving sovereignty. Open source gives you control over the stack. You're not dependent on a foreign vendor's proprietary system. You can audit the code. You can modify it for your needs. You can ensure it complies with local regulations. But even with open-source software, you still need power. And that's where energy policy becomes crucial. If European countries want to maintain competitive AI industries, they need to ensure adequate energy supply for AI workloads. This means investment in grid infrastructure, policies that prioritize energy allocation for strategic industries, and potentially incentives for energy-efficient AI development. Otherwise, sovereignty becomes academic because the workloads simply move to wherever energy is available. Here's something that often gets lost in all the technical discussion about energy and infrastructure: the human element. As AI systems become more autonomous and more energy-intensive, the way humans interact with these systems becomes critically important. Because ultimately, the return on that energy investment depends on whether humans can effectively leverage what the AI produces. We're seeing a recognition that AI tools ignoring human nuance are fundamentally limited. Tone, temperament, personality, communication style. These factors dramatically affect how people engage with autonomous systems and how effective those systems are in collaborative environments. There's emerging work on AI systems that can detect workplace conflict before human managers even recognize there's a problem. Systems that understand communication patterns, influence dynamics, trust building, and motivation. This isn't about replacing human judgment. It's about giving humans better information to make decisions. Think about the energy efficiency angle here. If an autonomous AI system makes perfect technical decisions but does so in a way that creates friction with the human team, you're wasting energy because the system's outputs won't be effectively implemented. Conversely, if the AI can adapt its communication and decision-making style to work effectively with the specific humans in the loop, you get much better return on the energy invested. Personality science and behavioral understanding are becoming part of how we architect autonomous AI systems, ensuring they're not just technically capable but also effective collaborators. This human integration challenge also affects how organizations need to think about talent. You can't just hire data scientists anymore. You need people who understand the interplay between autonomous systems, energy constraints, organizational dynamics, and domain expertise. You need governance frameworks that allow humans to govern the governance, overseeing autonomous systems that themselves manage other systems. This is a fundamentally different talent profile than what most organizations have built for traditional IT or even for early-stage AI projects. So let's bring this full circle. The era of AI as an experimental technology, as a chatbot curiosity, as a content generation toy, that's over. What's coming in 2026 and beyond is AI as autonomous infrastructure, systems that execute complex workflows with minimal oversight, make consequential decisions, and fundamentally reshape how businesses operate. But this transformation is constrained by something most people aren't paying attention to: energy. Not model parameters, not training data, not algorithm sophistication. Energy from the grid. The companies that understand this, that architect for efficiency, that secure access to power, and that deploy AI where it creates genuine value, those companies will thrive. The ones still chasing the largest models and the flashiest demos without thinking about the energy economics? They're going to hit a wall. And that wall is coming fast. The question is, which side of it will you be on?